You know, there are these quiet, almost invisible forces that make our world tick. Today, we're going to dive into one of the most powerful and honestly underappreciated of them all, capillary action. It's a phenomenon you rely on every single day, probably without even realizing it.
Okay, so let's start with a puzzle. I want you to picture a giant sequoia tree, just towering hundreds of feet into the air. It needs to get water all the way up to its highest leaves to live, but it doesn't have a heart, no muscles, no mechanical pump. So how in the world does it pull that off? How does it defy gravity on such a massive scale?
And now for the twist. What could that ancient biological puzzle possibly have to do with the super high-tech challenge of, say, managing liquid fuel in zero gravity on a spaceship? Well, the answer to both of those questions is actually the same. It's the same subtle but incredibly powerful principle at work.
To crack this mystery, we first have to get a handle on the unique properties of water itself. And really, it all boils down to this kind of molecular stickiness that comes from a few key forces. First up, you've got cohesion. It helps to think of water molecules as tiny little magnets. They're super attracted to each other. They always want to clump together. This is exactly why water forms beads and droplets. It's just all those water molecules pulling inward on their neighbors. Then you have adhesion. So if cohesion is water sticking to itself, adhesion is water's ability to stick to other stuff. Like the inside of a plant stem, a paper towel, or the side of a glass tube. It's the very reason things get wet.
And when you mix these two forces together, especially that powerful cohesion, you get something called surface tension. It's like an invisible skin on the surface of water that's so strong it actually lets insects walk right on top of it. The molecules on the surface are just pulling on each other so tightly that they form this amazingly resilient film.
So how does this all come together? Well, imagine you stick a really narrow tube into a glass of water. Adhesion makes the water molecules literally grab onto the walls of the tube and start to climb. And because of cohesion, they pull their buddies along for the ride. Now, in a skinnier tube, there's more wall surface for the water to grab onto, which means adhesion's upward pull can overpower gravity and lift that whole column of water even higher.
And that right there is the magic moment. When you put adhesion, cohesion, and surface tension together inside a tiny space, what you get is capillary action. It is the engine that lets liquids crawl through porous materials, seemingly breaking the laws of gravity.
Okay, and once you know what you're looking for, you start seeing this force absolutely everywhere. It's not just some obscure thing in a science lab, it's a fundamental part of our daily lives. I love this quote from the U.S. Geological Survey because it's so true. The next time you grab a paper towel to clean up a spill, you are literally commanding this powerful force. That towel is just a huge network of tiny little gaps between its fibers, and those gaps are the perfect pathways for capillary action to just suck that water right up.
You see it when plants pull water out of the soil through their roots. It's happening in the corner of your eye, where tiny ducts use it to drain away tears. And hey, if you've ever used a fountain pen, that's capillary action at work, carefully guiding the ink from the cartridge down to the tip of the pen.
And you can actually make this whole invisible process totally visible with a super simple experiment. Just stick a stalk of celery in some colored water. After a few days, you'll see that color has traveled all the way up to the leaves. You're literally watching the plant's tiny little water tubes, its capillaries, pulling that water upward against gravity.
All right, so let's circle back to our big mysteries. How does this simple, elegant principle allow both Mother Nature and rocket scientists to pull off these incredible feats of engineering?
So that 300-foot tree, how does it do it? Well, capillary action is the critical first step. It gets the water from the soil into the root system. But to get it all the way to the top, it needs a partner. As water evaporates from the leaves way up high, the powerful cohesive bonds between all the water molecules pull the entire column of water up from below. It's like a single, unbroken chain being hoisted hundreds of feet into the sky. Now for the rocket. This is where it gets really interesting. Here on Earth, gravity is a huge deal, and it usually limits capillary action to just a few millimeters. But in space, without gravity constantly pulling everything down, capillary forces suddenly become the dominant player. All of a sudden, this quiet little effect can move and control large amounts of liquid over several meters. It's a total game changer.
And this is exactly why NASA is so obsessed with figuring it out. They've run specific experiments like this capillary channel flow project on the International Space Station just to understand and learn how to harness this force. For long space missions, mastering it is absolutely critical.
So, in a spacecraft, engineers design these fuel tanks with special grooves and channels built right in. Capillary action makes the fuel or the water cling to the walls of these channels, guiding it precisely where it needs to go. This system makes sure that no stray gas bubbles get sucked into the engine's thrusters when they fire, which, yeah, would be catastrophic.
And the power of this force isn't always about speed. In fact, sometimes its real power is in how slow and steady it is. In certain types of fine-grained clay soils, the pull of capillary action is so persistent that it can take over 400 days for water to climb to its maximum height. It's a slow, relentless, and incredibly powerful force in geology.
Okay, now to really appreciate just how elegant capillary action is, let's take a quick detour into a completely different field: quantum physics. Trust me, there's a pattern here that's just too cool to ignore.
So in a 2017 paper, scientists were describing a phenomenon in certain materials where the overall structure seems perfectly symmetrical and balanced, but hiding inside are these localized, asymmetrical forces that create really powerful effects. Sound familiar?
They called it spin layer locking. And what that basically means is you have a material where these tiny opposing forces at the atomic level are perfectly balanced against each other. So the material might seem neutral on the surface, but this hidden tug-of-war gives it unique and powerful properties. It's a beautiful parallel, right? Just like capillary action comes from the battle between adhesion and cohesion, incredible things can emerge from other hidden balanced forces in the universe.
So, when you add it all up, what do you get? Capillary action is nothing short of an unseen superpower. It's this quiet, relentless force that is constantly at work, shaping our world from the microscopic all the way up to the astronomic.
I mean, this is the link between the tallest living thing on our planet and the technology we build to leave it. It's a perfect example of a fundamental physical principle being used by both the genius of nature and our own most advanced inventions.
This force dictates how paint sticks to a canvas, how your body absorbs nutrients, how morning dew clings to a spider's web. So the next time you see water climbing or clinging or cleaning something up, just take a second to appreciate this hidden superpower. And it makes you wonder, what else in our world is quietly being shaped by it?